Alright, in order to solve this problem, you will have to start out with drawing a free body diagrams. My free body diagram is a little bit uh, complicated, but it's just pretty much for your reference. But all you need to draw is this white arrow lines right here to represent the free body diagram. We know that the box is resting on the surface of an incline, so therefore there's a normal force point perpendicular to the surface. We also know there's a friction force pointing up the incline, and also there is a component that going down incline due to the force of gravity. This is the mg sine theta and mg cos theta. You can watch the video up here. I will show you how I came up with the equation for those components in this video up here. But for now, this is a free body diagram. And again, you don't need to draw these dotted lines. You don't need to draw um, anything here except for this arrow, that, and then the weight arrow downward. So what is it that we're looking for? We need to find the time in the problem that asks you for the time. Okay, let's see. If the box released from rest from the top of the ramp, how much time does it take to reach the bottom? So that's what interesting. And what is the second part of the question will ask you about, okay, what is the coefficients of static frictions, the minimum, okay? And we can solve that later too. Given, what is given to us? It given us the angle of 35 degrees and also give us the distance of the ramp, which is 2 meters. And then we have mu, whether it's static or kinetic. They just gonna say that's 0.02. And mu doesn't have any units, so it's just a number. So to solve this, we think back about what we learned about kinematic equation. You can start out with Newton's law, then use kinematic, or you can start out with kinematic and then use Newton's law. But for this problem, I decided to use kinematic first. I'm interested in finding time, and there's two kinematic equations that I have shown you in the early video to help solve this type of problems. And the derivation of this kinematic equation is again up here in the corner. You can click on that to find out how I come up with these equations. So let's begin. So we have the starting velocity is 0 because on a box it starts from rest. So we just remove that, it becomes 1/2 a xt squared. And as you can see, my coordinate system here, x is pretty much, the x-axis is up and down incline. So that's why I'm labeling f(x), okay? And so t is something that we're interested in. That's why I put it in red. So you can manipulate the algebra a little bit, and if you take the square root of 2x divided by ax, that will give you a t. The issue here is we don't have the acceleration down the incline. So we need to use Newton's second law to figure that out. Newton's law always going to give us the acceleration. With the accelerations, you can pretty much solve the problems here. So let's go to Newton's law. Newton's second law states that the force, the net force in the x direction here equal to mass times acceleration in the x direction. We're not going to deal with the y directions because we know that it is the net force in the y direction is 0 because the magnitude mg cos equal to the normal force right here. As you can see, if not, what happens if the y component force is not equal? Then the object will accelerate through the surface or just accelerate up, and we know that's not the case. Okay, we know that it just go up, go down incline, so we can ignore the y components. So mg sine theta is this component right here, and we define as a positive vectors. So then the force of friction, which is mu n, is a minus, so I put a minus sign. That will give us mass time acceleration. And so the question then is, okay, what is the normal force? Just looking at this free body diagram, we should know that the normal force is equal to the magnitude of this blue vector right here, which is mg cos. So I'm just replacing normal force with mg cos theta, and that's the mu. Okay. So clean up my algebra. I pulled out mg, and I noticed an m on both sides, so I remove that m, and the equation become g sine of theta minus mu cos of theta. Okay. So the rest is just plugging in the number. So 9.8 is the acceleration of gravity. It's not giving you to you in a problem, but it's expected that you know that any objects uh, falling near the Earth's surface is we assume it has well, it is has an acceleration of 9.8 meter per second square. And so I just plug in the angle and the mu, and it will give me, if I plug in everything correctly in calculator, it will give me 4 meter per second square. Please be aware that on the graphing calculators, if you don't put it in degrees, if you put it in radians, you will not get the same answer that I'm getting. So don't forget to do that. Hopefully your math teachers have taught you that you need to change the mode in your graphing calculators in order to put it in degrees. So you have AX equal 4 meter per second square. So the rest is just taking this value and plug into this equation right here, 4. And therefore you can find for T, and T is 1.0 seconds. So we done solving the first problem, right? First problem asking you for the time and you solve it. So the next question asks you about mu. You say, wait a minute, didn't they give you the mu, the coefficient of frictions? The second problem, they changed that a little bit. Second problem, they say that, you coat it with resin to make it less slippery. So they changed the mu. That's why it's no longer a given for the second problem. It's something that we need to figure out. Then it's not too complicated. We already going to use Newton's second law, so let's just use Newton's second law. The sum of the force and extractions equal to mass acceleration extractions again, which is mg sine theta down the incline, the component, the force down the incline here, and we have mu n, which is the normal, is the friction force right here. And again, the reason I put in red because in the second problem is not a given. It's something that you need to find. So then you ask yourself, okay, so if it is, let's see here, we want just enough resonance box that it does not slide down the ramp. So it's at rest. Because at rest, so therefore the combination of all the force equal to each other, then so therefore it's equal to 0, right? It says at rest. It's not moving yet. It's not slipping down the incline yet. So it must equal to each other. And so I can just put the normal force in, the magnitude of normal force equal to mg cos theta. Okay, so what you need to do next is you need to put mu by itself. Put this equation to the right and divide both sides by mg cos theta. Actually, I don't need to. As you can see here, we have an mg over to the right and mg to the left. We can cross that out, equal to sine theta and cos theta. And this is just some mathematics. Take sine theta divided by cos theta, that will equal to mu. If you want to clean that even more, it just becomes tangent. Okay, you can plug in the number and you get the answer. But if you want to clean this up, you can just call the tangent of theta equal to mu. And so you put 35 degrees in, and that will give you around 0.7 for the coefficients of frictions. And then that's pretty much it for this problem. That's the answer. I will see you in the next video.